Imagine a world where interstellar travel takes just days, where the vastness of the universe is at our fingertips, and where the laws of physics as we know them are defied. Does this sound like pure science fiction? For many years, it was. But what if I told you that we are now closer to realizing this dream than ever before? The idea of traveling to another star system in a matter of days has long captivated the human imagination, a notion firmly planted in the realm of science fiction. Today, however, we stand on the brink of a breakthrough that could turn this dream into reality. Scientists are making warp drive more feasible than we ever thought possible. The concept of faster-than-light travel has intrigued scientists and dreamers alike for decades. While the theoretical groundwork for warp drive has been laid out in mathematical equations, practical implementation has remained elusive. The idea that we could someday traverse the cosmos at speed surpassing that of light itself has fueled countless science fiction stories and inspired generations of researchers. Until now, warp drive has been seen as a mere fantasy, an imaginative speculation with no basis in our physical reality, yet, recent developments suggest that we may be closer than ever to achieving this seemingly impossible feat. The feasibility of faster-than-light travel has long been proven mathematically, but translating these calculations from theory to reality has presented a formidable challenge. The primary obstacle has always been the enormous amount of energy required to create a warp bubble, a region of space that could theoretically allow a spacecraft to travel faster than light. For years, this energy problem has been the Achilles heel of warp drive research, a barrier that seemed insurmountable. According to Albert Einstein's theory of relativity, nothing in the universe can travel faster than the speed of light in a vacuum. This fundamental principle has been a cornerstone of modern physics, and it has posed a significant challenge for those attempting to devise methods of superluminal travel. The speed of light, approximately 299,792 km per second, or about 186,282 miles per second, is the ultimate speed limit in our universe. So, how could we possibly transport a spaceship and ourselves through space and time at speeds exceeding this cosmic limit? Science fiction writers have long imagined a solution to this problem. More than 70 years ago, they envisioned spaceships capable of creating a space-time distortion, allowing them to glide through the fabric of space and time without actually overcoming the vast distances between stars. This concept, known as the warp drive, essentially tricks Einstein's physics by circumventing its laws. The idea is to slip a spaceship through a fold in spacetime, compressing space in front of the ship and expanding it behind, effectively creating a bubble in which the ship can travel faster than light. In popular science fiction formats such as Star Trek, the heroes activate their warp drive, and the spaceship appears to dissolve into time and space, only to reappear moments later at a distant point in the universe. For a long time, scientists dismissed this as pure nonsense, a fanciful idea with no basis in reality. However, a few brave souls set out to test whether warp drive was theoretically possible, and they found that it is, at least in theory. The warp drive mechanism hinges on the creation of a warp bubble. This bubble is a region of spacetime that is distorted in a way that allows the spaceship within it to travel faster than light. The basic idea is to compress space in front of the spaceship and expand it behind, effectively reducing the distance the spaceship has to travel. This compression and expansion of space create a warp bubble, within which the laws of normal physics are temporarily suspended. The concept of a warp bubble was first proposed by physicist Miguel Alcubierre in 1994. Alcubierre's groundbreaking paper described a theoretical model in which a spacecraft could achieve faster-than-light travel by distorting spacetime. The spacecraft would ride within a bubble of flat spacetime, while the spacetime around the bubble would be contracted in front and expanded behind. This would allow the spacecraft to move faster than light relative to the space outside the bubble, without violating the principles of relativity. However, there was a major problem with Alcubierre's model. The energy required to create such a warp bubble was astronomical. According to his calculations, the amount of energy needed to warp spacetime in this way was equivalent to the mass energy of the entire observable universe. This made the practical implementation of a warp drive seem impossible. The energy problem has been the most significant barrier to the development of warp drive technology. Creating the spatial distortions necessary for a warp bubble requires an enormous amount of energy, far beyond what we can currently generate or even conceive of generating. In Alcubierre's original model, the energy needed was so vast that it seemed impossible to achieve with any known or conceivable technology. Researchers have been searching for a solution to this energy problem for decades. Various proposals have been made, ranging from the use of exotic forms of energy to harnessing the power of quantum fluctuations. However, none of these ideas have provided a viable solution. Exotic energy forms, such as negative energy or exotic matter, have been theorized but not observed in reality. These forms of energy are purely hypothetical constructs, and we have no way of generating or harnessing them in the foreseeable future. Enter solitons, stable, self-sustaining waves that can travel over long distances without losing their shape or energy. Dr. Erich Lenz, a physicist from the University of Göttingen in Germany, proposed that solitons could be the solution to the energy problem plaguing warp drive research. Solitons are a special form of energy transfer, and they have unique properties that make them ideal for this purpose. In nature, solitons are stable waves that maintain their shape and speed over long distances. They occur in various environments, from water channels to optical fibers. In telecommunications, solitons are used in fiber optic cables to carry signals over long distances without loss of shape or speed. In quantum field theory, solitons are so stable that they exhibit particle-like properties, even though they are waves. This duality between wave and particle makes them a fascinating and versatile phenomenon. Dr. Lenz's idea was to use solitons to create a warp bubble. Solitons can conduct energy in a way that reduces the overall energy demand, making it feasible to generate the necessary spatial distortions. By harnessing the stability and self-sustaining nature of solitons, we could potentially create a warp bubble with a fraction of the energy previously thought necessary. Solitons are not matter in the classical sense, nor are they pure energy. Instead, they are a special form of energy transfer. These waves were first discovered in the 19th century when a scientist observed extremely stable waves in water channels. Since then, solitons have been studied extensively and used in various applications, from telecommunications to quantum field theory. In the context of warp drive, solitons offer a promising solution to the energy problem. Their stability and self-sustaining nature mean that they can maintain their shape and speed over long distances, making them ideal for creating and sustaining a warp bubble. When used in fiber optic cables, solitons carry signals without losing shape or speed, demonstrating their potential for long-distance energy transfer. In quantum field theory, solitons exhibit particle-like properties, despite being waves. This unique characteristic makes them an intriguing bridge between wave and particle, between potential and matter. In the realm of quantum mechanics, quanta are waves until they are measured and become particles. Theoretically, quanta exist in both states simultaneously, but to us, they appear as solid matter when measured. This duality of waves and particles is one of the mysteries of quantum physics and may hold the key to unlocking new dimensions of spacetime. Historical and current research. Solitons have a rich history in scientific research. Their discovery in the 19th century marked the beginning of a new understanding of wave phenomena. Over the years, solitons have been studied in various contexts, from fluid dynamics to optics and telecommunications. In the latter field, solitons have revolutionized data transmission by enabling the efficient transfer of signals over long distances without distortion. In recent years, solitons have garnered interest in the field of warp drive research. Dr. Erich Lenz's proposal to use solitons for creating a warp bubble has sparked renewed hope in the feasibility of faster-than-light travel. His work builds on the theoretical foundation laid by Miguel Alcubierre and other physicists who have explored the possibilities of warp drive. Dr. Harold G. Sonny White, a former top scientist at NASA, has also made significant contributions to this field. Dr. White discovered a natural warp bubble while investigating the structure of Casimir cavities. This discovery was serendipitous, as Casimir cavities were originally studied for a completely different purpose. The Casimir effect, which occurs when physical forces act between two closely spaced metal plates, resulted in the formation of a natural warp bubble smaller than 1 mm. This finding provided concrete evidence that warp bubbles could exist in nature and be created with positive energy sources. While the theoretical foundation for warp drive is being solidified, practical implementation remains a challenge. Several technologies could be combined with soliton technology to create a functional warp drive. Among these are ion thrusters, solar sails, and nuclear propulsion systems. Ion thrusters are known for their high efficiency and are ideal for long missions in space. They work by electrically accelerating ions, which generates thrust. This technology has already been used in missions like the Voyager probes, which have been traveling through the universe for more than 45 years. However, ion thrusters offer relatively low thrust, resulting in slow acceleration over long periods. While this makes them suitable for long-duration missions, it poses a challenge for achieving the rapid travel needed for interstellar journeys. Solar sails utilize the pressure of photons emitted by the sun or other light sources to propel spacecraft. This technology is particularly efficient for long-distance travel and requires virtually no fuel. Solar sails are made of very thin materials and operate best in low-mass configurations. They can extract enormous potential from small amounts of light, allowing spaceships to recharge on stars and cover vast distances with an almost infinite charge. When combined with soliton technology, solar sails could become a powerful tool for interstellar travel. Nuclear propulsion systems, while controversial, offer significantly higher thrust compared to ion engines or solar sails. These systems have been considered for upcoming space missions, such as flights to the Moon and Mars. Nuclear propulsion could provide the necessary thrust for interstellar travel, but the presence of radioactive reactors on board poses risks and challenges. Despite these concerns, nuclear technology remains a potential solution for achieving the high thrust required for warp drive. The future of warp drive technology is promising, but significant challenges remain. The technical and energy requirements are considerable, and practical implementation is still decades away. However, the progress made in recent years suggests that we are on the right track. Dr. Harold G. Sonny White's discovery of a natural warp bubble and Dr. Eric Lentz's proposal to use solitons have opened new avenues for research. By combining their work, we could unlock entirely new realms of physics and bring warp drive closer to reality. Current estimates suggest that we may see the first prototypes of a fully functional warp drive within 10 years. As we continue to explore the possibilities of warp drive and faster-than-light travel, the potential for human exploration of the cosmos grows. Stay tuned for the latest advancements and groundbreaking discoveries in this exciting field. Subscribe to the channel now and be part of every new video, as we embark on this journey to the stars and beyond.